Yeah, so this is a bit of a whirlwind tour of Bayesian deep learning. It's a huge area. I think, I'm not sure what's the situation now, but for quite a number of years, it's like one of the biggest workshops at the major conferences, NeurIPS, ICML, and so forth. There's lots of interest in this, and there's a lot of interesting work happening here, so which I'd like to kind of hopefully talk about some of the more recent work as well. So, but this is more of a tutorial. There's not really any kind of like, newfangled research that just published last year or something, okay? Cool. So if you have any questions, do ask me. I'm happy to take questions. So I probably realize that the slides probably have maybe sometimes quite a bit of equations. It's, I won't be going through the equations very in detail, but I figured that it's good to have that reference for you, and I'll try to also put in lots of references throughout the slides as well if you want to look up textbooks or papers and so forth. I'd like to ask actually, are people here familiar with probability and statistics? Can you raise your hand? Okay, great, okay, cool. So I ask because I'm using quite a lot of notations in probability quite liberally. And because it's quite a short lecture, I won't be able to kind of go through the axioms of probability, like the rules of probability, okay? Cool, so I'll start with, before I go into Bayesian deep learning, which is the second half of the lecture, I'll start a bit about Bayesian machine learning in general. It's kind of like looking at the broader picture. Okay, so if you think about machine learning as a research area, there's kind of like, in a sense, two different types of research that's happening. Okay, so one is machine learning as technology. We're building tools, we're building software infrastructure, hardware infrastructure to do AI. Okay, and also to use this to solve lots of problems in industry, business, in society, and so forth. Okay. There's also another branch of machine learning, which is about machine learning as a science. It's about understanding what's really going on in the learning process. Okay, and what we're interested in is, understanding what are the kind of fundamental principles that kind of govern learning and intelligence. Okay, and in that sense, it has lots of relations, not just to computer science, but also to other fields that have to do with learning and intelligence. So, for example, neuroscience, cognitive science, statistics, signal processing, and so forth. And there's a huge kind of area there that people are really trying to understand what's going on under the hood, in a sense. Okay, and you can think about Bayesian machine learning as a particular normative theory of learning and intelligence. It's normative in the sense that it's what you would do if you have all the resources in the world and if you have access to all the data. Okay, and it's also normative in the sense that, so there's a bit of this joke in Bayesian machine learning where whatever thing you do that somebody else came out with that works, a few years later somebody will have a paper that says a Bayesian interpretation of this thing that works. Okay, and the reason for that is because if the thing really works, there must be some underlying principle, and basically this kind of Bayesian approach is kind of one way in which that underlying principle comes about. Okay, that's why everything that works is Bayesian in some sense. Okay, so it's a bit of a joke. Okay, so one of the issues I think with Bayesian machine learning is that it does have lots of interesting methods that are developed, but not necessarily all the methods would necessarily work. But it's still kind of good to think about it as this kind of like theory of how we should be doing learning and intelligence. Okay, and something else which I'd like to say is that there's been lots of successes of Bayesian methods, not just in machine learning, but across lots of different fields. Okay, so I talked about kind of coming out of the pandemic lockdowns. During the pandemic, I was involved in some research working with the Royal Society in the UK in terms of helping government science advice, right? And one of the things that I kind of noticed about that is actually that, we have lots of excitement around machine learning and deep learning, but actually a lot of that work and technology didn't really change the trajectory of the pandemic very much. But what really did change the trajectory of the pandemic is actually things like Bayesian statistics, because people use these tools to understand what's going on the ground, across the population, across the whole world, how is the pandemic developing, and so forth. Okay. Yeah. Okay. Cool. So here we're here because we're interested in, of course, not statistics, but rather about machine learning and artificial intelligence, right? So in AI, we are kind of, the general setup is, we have an agent that's acting in some environment, right? And the agent can take actions, it can make predictions, and it interacts with this environment in that these actions are changing the environment in some way. Okay? And the agent also has sensory devices that receives observations from the environment that tells it something about what's happening in that environment. And maybe there's also rewards as well. So, we have a whole day of reinforcement learning where you learn about different ways in which RL agents can interact with environments in an efficient way. Okay. So if you think about this process of the agent and what the agent knows about the environment and what the agent doesn't know about the environment, and how it should use that knowledge to act in that environment. Okay. And in a sense, Bayesian machine learning is about, well, how do you go about doing that? Okay. Ooh, okay, sorry. I realized that this slide is cut off a bit on the side. Right, so, and the overall idea of Bayesian machine learning is really in the agent's head. Okay, it's gonna construct a model of how the environment operates and how, and then once it has this model, it can then do things like infer what are the things that it did not observe from the things that it did observe about the environment. It could learn about how the environment operates, and then it could also act in that environment, take actions in that a model as well. Okay, in a sense, guided by the predictions of the model. Okay. Cool. So so this is and in a Bayesian machine learning, basically a model is basically some joint distribution over random variables, some of which represents the things that you observe about the environment, and some of which you represent latent variables, or things that you think is out there, but you don't really observe directly. Okay. So I'll just kind of introduce a bit of notation. So we have observations are going to be things that we see in the environment. So I'm going to denote that by Y. Okay. And these observations could be obtained in some context. So, and that context is going to be X. Okay. So context could be things which are related to an environment, but you're not going to directly model. So for example, actions that you took in the previous time step. Okay. We also have latent variables. So these are the things that are in the environment. We think is in the environment, but we're not going to directly observe, so we don't fully observe them. And then finally, we may have some parameters which describe the environment itself. Okay, so those will be theta. And basically, a model is a joint distribution over all of our latent variables, all of our random variables, whether observed or not observed. Okay, so we have a joint distribution over theta, z, and y, conditioned on x, which we're not going to model. That's why we're conditioning on it. And so for simplicity, I'm just going to assume that this joint distribution is basically some prior distribution over theta. Okay, and I'll talk about what does the prior mean later. But basically, it's some distribution over theta times this is a product of the probability of Zi. So I from 1 to n. So this is going to be our data set. So Zi given theta and Yi given Zi and Xi and theta. Okay, and basically we're assuming that conditional on theta, our data set is going to be independent and identically distributed. Okay. Right. So there are, a few things here. So we have the prior, and what the prior is really kind of telling us is, before we observe anything about the environment, what do we think are the likely parameters that describe the environment? Okay. So this could include things like, simplicity assumptions, smoothness assumptions, and so forth. So basically, thetas that give rise to simpler models or smoother models will have higher probability under our prior. Okay. And something else, a term that people often use is likelihood, and the likelihood is basically the probability of the observation under our model. Okay. And sometimes we might call something called a marginal likelihood, where we marginalize out the latent variables that we don't observe. Okay. So that's why I kind of like dropped that random variable here. So this thing here is called a graphical model. It used to be that everybody who does machine learning, this would be one of the first things that they learned about 20 years ago. But nowadays we learn about neural networks, but maybe not as much about graphical models. But basically in a graphical model, each node here in our graph is some random variable. The shaded nodes are basically not random, we observe them. Okay? And the arrows denote dependencies between the random variables. Okay? And sometimes we have a plate like this, which basically means that we are repeating that bit of the graphical model n times in this case. Okay. Cool. Let me time this. Okay. Any questions about this so far? No. Okay. It's still quite just in the beginning, I guess. Right, so just to give you some examples, okay, so for most of this talk, we talk about Bayesian deep learning. In Bayesian deep learning, the typical approach would be that the theta would correspond to your neural network parameters, okay. So they are describing, given some inputs x, what the outputs should be, okay. So that's your environment, basically, okay. So we want to predict y given x, and our neural network tells us how do we make that prediction. And in this case, there are no latent variables, so z is just nothing. Okay? But there are other situations where you could have latent variables. Okay? So for example, in epidemiology, theta might correspond to the reproduction number of your disease. So how quickly does the disease, or rather, on average, how many people get infected by a person who actually got that disease, okay? So that's the reproduction number. We don't observe the reproduction number, but we do want to infer it from the data that we have, okay? And in the generative process, the way the reproduction number relates to the observations that we have is through, so this is a very simple case, okay? So z here is our latent variable. We don't actually observe it, okay? It's the number of actual transmissions in the population. So how many people gets infected, okay? But we don't actually observe that number. What we do observe is, given that this number of people did their COVID tests, maybe in the hospital or maybe at home, y is the number of positive tests, okay? And so in this case, we do observe the number of positive tests. We don't observe the number of transmissions, and we are trying to infer the reproduction number. Okay, so this would be an example of a Bayesian model in epidemiology. Okay, so what are the things that you like to compute given such a model? Okay, basically there are a few things, but one of the most important things is to compute what people call posterior distributions. Okay, so these are simply conditional distributions of your latent variables given your observations. And this is just applying Bayes' rule from probability. Okay, and that's why it's called Bayesian learning. It's based on Bayes' rule. Okay, and yeah, so conditional on our observation y and the context x, the conditional distribution of theta given this is just given by Bayes' rule. It's the product of the prior times the likelihood, and then we have a normalization factor to ensure that this distribution over theta sums to 1. Okay. And you can think of this as the following way. So we have products between a prior and a likelihood, okay? And values of theta for which we have high posterior probability would have to have high prior probability and high likelihood, okay? And so what that is saying is that the values of theta, which has high probability under our posterior, balances between our prior expectations about what are the likely environments which gives rise to our data. Okay, so this is our prior knowledge that we are kind of bringing in before we observe anything, and then also a high likelihood as well. So parameters which has high posterior probability has to explain the data well in terms of high likelihood, and has to conform to our prior knowledge about likely environments. Okay. There's another term which people use, is called inference, and inference is generally computing the posterior distribution not over the parameters which describe your environments, but rather the latent variables in the environment, conditional also on the environment's parameters. Okay, so yeah, so and in general in Bayesian machine learning, people use inference to mean just computing posterior distributions of stuff. Okay, so this is a different meaning than I think it was started by Jensen Huang, I think, in NVIDIA. He started calling computing predictions on tests at test time inferencing. But actually that was not the original notion of the word inference. Okay, so that could possibly create some confusion. Basically in Bayesian machine learning, inference simply means computing posterior distributions. Okay. Right, so while in deep learning, when people say inferencing, what they mean is prediction. So given your data set, this is boldface X and Y, okay? And given a new test input, what is the conditional distribution of the output given our data set and given the new test input? And manipulating the rules of probability, you can show that this predictive distribution is an integral over basically the probability of y prime, so our test output, given our neural network parameters and our test input, x prime, and then this integral is over the posterior distribution. Okay. So basically you can think of this as the posterior is, in a sense, likely explanations of the data in our data set, and this is an average over likely explanations and of the predictive distributions given theta. Okay? So the posterior captures both the knowledge gained from our data set and also incorporating our prior, but also it captures some residual uncertainty about theta. So there are, given a particular data set, there could be multiple thetas that explain that data set equally well. And what Bayesian prediction says is, if you have multiple explanations that explain the data well, you should average over those explanations when you make your predictions. Okay? And this is basically, yeah, so in a sense captures a bit of your uncertainty better than if you were to just use a single maximum likelihood estimates of your parameters. Okay. Right, so let's contrast this with regularized maximum likelihood. So in deep learning, typically what we would do is, given a data set, we want to find the parameters which has maximum likelihood and maybe regularized in some way. Okay? So you could write that, in fact, as basically the regularization, it corresponds to the prior on theta, and the likelihood is just the likelihood, okay? And we want to find the parameter which maximizes this regularized likelihood, and then given that parameter, we then make predictions with them. Okay, so in a sense, this regularized maximum likelihood is, you could think of it as an approximation of this integral, where you replace that integral over the posterior distribution with the one value of theta which has maximum posterior probability. But it doesn't really capture that uncertainty around possible explanations other than the maximum likelihood one. Okay. And this is particularly important when, coming back to the epidemiology example, when there are, in fact, lots of possible explanations for the same data that you observe, and it's important to average over them so that you don't make overconfidence but wrong predictions. Okay. Right. So we have predictions, right, of y prime given x prime and our data set, but that doesn't necessarily correspond to actions. Okay. So so there's actually a branch of Bayesian statistics called Bayesian decision theory, and I'll just kind of say just two sentences about it. Basically, predictions are not the same as actions. To actually take an action, what we want to do is to take actions which maximize utility, okay? And in fact, it's maximizing expected utility, okay? So given a test input and some test output, and if we take action A prime in this case, there might be some utility associated with that. Okay? And what we want to do is to take actions which maximize this expected utility under the what's called the posterior predictive distribution. Okay? So just to give you an example, X could be your mammogram, Y could be whether somebody has breast cancer, but so you have a machine learning system, it makes predictions based on the mammogram, but the action that the patient takes the action that the patient takes need not correspond exactly to the predictions of the machine learning system, because different patients could have different utilities associated with different treatment regimes. And that utility corresponds to the patient's preferences, basically. Okay, so you could have the same prediction, but one patient takes cause A, another patient takes cause B. Okay. Right. And yeah, so in Bayesian machine learning, basically a lot of the work that's involved is basically trying to compute these posterior distributions and also to compute the marginal probabilities where we integrate out the random variables which we do not observe. And this could involve the latent variables Z or both Z and the parameters theta as well. Okay. And unfortunately otherwise we'll all be Bayesians, but unfortunately, of course, this is what we would like to do, but we cannot actually do this. It's intractable. Okay, almost all models that are of interest, all of these things are going to be intractable to compute. So basically, a lot of work in Bayesian machine learning involves how do we approximate these quantities in a computationally efficient way. Okay, and I'll talk about some of these methods in the context of Bayesian deep learning. But before I do that, I'd like to say a few words about, again, why Bayesian machine learning. Okay, and I was, in addition to successes across different fields, I'd like to kind of say kind of two reasons. Okay, these are in a sense more theoretical reasons. The first one is what's called a Dutch book. Okay, so imagine that the environment is a casino. Okay, and in the casino you can bet on coins. Okay, and there's some bias in that coin. Okay, heads or tails with some probability, and the probabilities need not be 0.5. So there's something that you want to infer based on the coin tosses that has happened in the past. Okay. And suppose that there are two people who walk into this casino. Okay, and one of them was deciding to bet $1 on heads because they think that heads gonna win. And the dealer at the casino at the time thought, well, I don't think it's going to be heads. I think it's going to more likely be tails. So I'm willing to give you a good odds, a good outcome if it turns out to be heads. Okay. So if I bet if the first person bets $1 on heads, and if it does turn out that the next coin toss was heads, then the person will win $3, okay? Because the casino doesn't think that it's going to be heads. And then if, of course, it turns out tails, then the person just loses the $1, okay? And then maybe 5 minutes later, another customer comes in, but maybe the dealer has changed shift, and the next dealer comes along and says, well, I think it's actually going to be, it's more likely that the next coin toss is going to be heads. It's not going to be tails. But this customer wants to bet $1 on tails, so the dealer gives the customer, the second customer, another deal, okay? You can win $3 if it does turn out tails, and you will lose your $1 if it turns out heads, okay? Of course, this little example is trying to illustrate that the two dealers had two different conceptions about whether the next coin toss is going to be heads or tails, okay? And they are inconsistent with each other, okay? And basically, if somebody is smart and they realize that there are these two inconsistent deals that they could bet on, instead of betting on only heads or only tails, the customer could bet on both heads and tails. Okay? So spend $2, one on heads, one on tails. And the great thing is, well, you always win $1, no matter what the outcome is. Okay? And this is what's called a Dutch book. Basically, it's something that could cheat the system if you realize that the system is inconsistent. And basically, so this is called a Dutch book. And basically, the only way in which you could reason about a set of phenomena and be willing to take bets on your reasons, the only way in which there's no Dutch book is if your reasoning is Bayesian. Okay, so this is, in a sense, a theoretical justification for why we want to use the Bayesian approach to reason about observations and uncertainty and so forth. Okay, so that's one reason. Another reason is actually something called Cox's theorem. And basically, what this is saying is that, we want to reason about some environment and some unobserved things in that environment, okay? And we may have some beliefs about what are the likely states in that environment. So I'm going to represent that belief with B. It need not be probabilities, it's just some beliefs. And basically, we're going to assume that B of X is the strength of our belief in statement X, and B of X given Y represents the strength of a statement in statement X, given some information which we observe, which is Y. And basically, Cox's axioms are a number of, in a sense, quite common sense assumptions about how beliefs should operate, okay? And basically, under those axioms, you could show that if a belief system satisfies these axioms, but then it must be equivalent to some probabilistic system, i.e. the beliefs are in one-to-one correspondence with some probabilities under some joint distribution. And so, and the way you would manipulate beliefs is via basically Bayes' rule, okay? Right. So this brings us to something which is very contentious. Okay, so there's in the stats community, there's arguments between the Bayesians and the frequentists, and basically these arguments boil down to what do the probabilities actually mean. Okay, so in the coin toss example, the coin is right there. There's some bias to that coin. Okay, there's no uncertainty in that. There's just, it's a physical system, and there's some number which represents the bias of that coin. It's just that we don't know what that number is, okay? And basically, the states of the environment and the properties of the environment can be deterministic, while in a Bayesian system, these things are treated as random or stochastic, okay? And so the probabilities aren't, in a sense, real probabilities. It's just probabilities that are just in your head, and they represent subjective beliefs. Okay, and basically Bayesians like this idea of subjective beliefs, while frequentists say that, well, these things are not random to begin with, there shouldn't be probabilities associated with them. Okay. Right, any questions about this before I go on to, yes?
So a question about Cox's theorem. What exactly does it mean for a belief to vary sensibly and much?
Sorry. Okay.
Right. So the common sense, what exactly does it mean for a belief to vary sensibly and much?
Right. So I think, can we take this? So the question is, what does that common sense axiom mean? Okay. And I would like to take this offline, if that's okay, because it might be a bit too detailed, and I realize that we're kind of running a little bit late, so we can talk about this after the lecture. Okay. There's another question. Yes.
Yes. So in models, you assume that the x's are independent of the thetas, right?
Yes.
Is that like a problem or?
So it's not that they are independent; they are simply not modeled as part of the joint distribution. Yeah.
But for example, in the immunology case, you have like the number of tests, right?
Mm-hmm.
And are the
Oh yeah. Yeah.
there should be a relation.
Yes, it's true. So the question is, why is X not model, and why is it independent of theta? So in this example, yes. So this is this is a very simplified assumption. We are assuming that the number of tests has nothing to do with the states of the environment, when in fact actually they do, right? Because when people see that, oh, number of COVID cases is rising, maybe I should do my test if I get a bit of a runny nose or something, and that has an effect. And so that's the hard thing with actually trying to model this appropriately, because we have people making decisions based on the data that they have. It's not necessarily the data that you have as well. Okay. Yes.
So if there is the extent variable z is always modeled based on the observations and never from the context or x?
Yeah. So z could also depend on x as well. That's fine. Yeah. So the question is why is z dependent on theta but not on x? On y. Well, basically, when you write down your joint distribution, you need some way of decomposing the joint probability as a product of conditional probabilities.
Because I think the assumption in contrastive learning on supervised learning is that the z is always dependent on x.
Yeah, so you could have the z's dependent on x. That's fine. So this is just a simplified model. Okay, so coming back to the epidemiology case, maybe they are not IID. There could be dependencies across days or time, right? And so you could have x, yt plus 1 dependent on yt, or zt plus 1 dependent on yt, and so forth, okay? And that's just kind of just additional complexities which you could incorporate in this framework, but I'm just keeping it simple in this case. Yes?
Maybe you could mention a couple of more practical tasks that using Bayesian approaches helps and outperforms the usual. Are there any practical examples?
Well, I think the pandemic was one example. So other examples, so for example, in neuroscience and cognitive science, one of the very successful theories for how the brain operates is actually, you can search for this, it's called the Bayesian brain. Basically that the brain operates by effectively Bayes' rule. And basically you can explain lots of different psychological phenomena like visual illusions and so forth by using Bayes' rule. So that's an example in which Bayesian inference was successful. I think there's also quite a lot of, so in astronomy, for example, people actually use Bayesian statistics a lot because they have a model of how the universe evolves over time, and they have observations about, well, how many galaxies of different types do they observe in the sky? and they want to know what are the cosmological constants which determine the evolution of the universe. And they actually use a Bayesian inference for doing that. Okay. Other examples, yeah, so there's kind of lots of examples. Yeah, I can think of, yeah, I've mentioned neuroscience, astronomy, epidemiology, I don't know. Yeah, so it's you know, it's quite a common sort of thing. So in social sciences, people use Bayesian statistics quite a bit in terms of inferring, you know, what are the determinants of outcome in terms of, you know, whether somebody is going to be successful in life, depending on, you know, their background, depending on how much access to education do they have, and so forth, right? So, yeah. Cool. I'd like to kind of get back to machine learning. Okay, so to Bayesian deep learning now. Okay. How many more minutes do I have actually? Okay. Okay. So still half an hour approximately. Okay. Cool. Good. So so we're here. We're interested in machine learning, and we're interested in deep learning. So what does Bayesian stuff have to do with deep learning? Okay. So as I said, in deep learning, we have some neural network, which I'm going to represent in a simple way. This is as a multi-layer perceptron, but it could be applied to different sorts of neural architectures as well. Our theta is going to be the parameters of our neural network. And given theta, we have the neural network parameterizing some function of our input, x. And we have our output, y. Our labels is going to be modeled as being distributed according to some conditional distribution given the output of the neural network. So in the classification case, f theta of x could be the logits for each of the class, and p of this p of y given x is simply a categorical distribution of the softmax of the logits. Okay. Right, and there are, I guess in a sense, 4 popular classes of approaches for doing, for computing this posterior distribution. As I said, you know, this is kind of, in a sense, underlies a lot of what we need to do in Bayesian machine learning. We need to compute the posterior distribution over the unobserved quantities, in this case, the neural network parameters, given the observed quantities, which is our data set of x's and y's. Okay. The simplest approach, which is basically regularized maximum likelihood, is called maximum a posteriori, okay? Because it's basically you take the posterior distribution and you want to find the single parameter theta which maximizes that posterior probability. Okay. And basically we're approximating this distribution over possible explanations of our data with a single explanation that is most likely. Okay. Of course, this is gonna undercount the uncertainty that we really have, and so if we can get some better approximations to the posterior, then we can maybe capture more of that uncertainty. Okay, but these are of course more intractable in this case, and this is I guess I'll talk about Laplace's approximation, variational approximation, and Markov chain Monte Carlo. Cool. Let's start with maximum a posteriori. So this is just regularized maximum likelihood, right? So if you look at the posterior probability here, you take the log on both sides. The denominator here is not a function of theta, so it turns into just a constant, right? So the log of the posterior probability of theta is some constant plus log of the prior plus sum over our data sets of the log of likelihood of each yi given each xi and the parameters. Okay. And of course, we all know this. We can actually find the most likely explanation which maximizes this regularized likelihood using optimization like SGD, Adam, and so forth. Okay, so SGD, a simple case, is we have an iterative algorithm where theta at the next iteration is the theta at the previous iteration plus a step size times a gradient which points uphill in this quantity which we want to maximize. Typically, we take the negative and we want to go downhill, but here I didn't take the negative, so we want to go uphill. Okay, and of course, this thing is still intractable because typically in machine learning, we are assuming that n is really large, so we cannot actually compute that gradient of that quantity by summing over all of our data set for every iteration. That's going to be too expensive, so we do things like mini batching, where we take a subset of our data set and we're going to approximate that the gradient of that likelihood term with the gradient only on that mini batch. Okay, so this is straightforward, right? So this is equivalent to regularized maximum likelihood, and as I said, it undercounts the uncertainty in our posteriors in our predictions. Okay, so there are lots of other methods which try to take this as a starting point and then try to actually somehow take into account better the actual uncertainty in our learning process. So for example, deep ensembles is a very popular method where instead of running this once and getting a single parameter out, a single parameter vector out, we might run this 20 times, each with a different initialization of our neural network. And we know that the likelihood landscape is very complicated for a neural network because of the nonlinearities. Each of these initializations is going to end with a different theta, and you just average over the predictions of the thetas. Okay, and what you can see is that where you have lots of data, each of those 20 thetas is going to give you the same prediction. But where you have less data, maybe when you do out of distribution generalization, each of those thetas is going to give you a different prediction. And if you average over them and also report the uncertainty across, or the disagreement across the 20 predictions, then that's going to give you a better predictions and also better calibrated predictions. So if you're uncertain, you can report that uncertainty. Okay. So that works really well. That's again referring to that joke I was talking about. Some people say that actually ensembles is Bayesian. Some people say no, it's not Bayesian. And there's a bunch of papers. If you're interested in this, I could point you in that direction as well. Okay, so myself, I've been involved in one of these papers. The title of our paper was Bayesian Deep Ensembles. Cool. Right, so that is maximum a posteriori. As I said, from the Bayesian perspective, it undercounts uncertainty. So are there other ways of actually taking into account better the uncertainty in our posterior? Okay. So, and Laplace's approximation is one of the oldest methods that people have developed. In fact, I think it dates back to Laplace, which is somewhat, I think, I'm not sure whether it's contemporary, maybe a bit after Thomas Bayes. Right, and Laplace's approximation says that basically instead of using a single explanation of our data, we're going to use that as our most likely explanation, and then we're going to capture the uncertainty around the posterior by fitting a Gaussian to that to the posterior distribution, centered at the most likely explanation. Okay, and effectively what this does is you look at the log of the joint probability over theta and y. So this is a function of theta, and we're just going to do a second order Taylor series expansion of this function of theta, so around the maximum a posteriori value of theta. Okay, so log p of theta and y is approximately log of p theta star and y plus the first order derivative term and a second order Hessian term as well. So this is just a second order Taylor series expansion. Okay. And if you do find that your theta star is actually one that is a local maximum in the posterior probability, then this second derivative is going to be negative definite. Okay? And basically, if you look at this thing here, this is basically the density of a Gaussian with a mean centered at theta star and a covariance matrix given by the inverse of the Hessian. And that's why the second derivative being negative definite is important, because this inverse is actually a covariance, and the covariance needs to be positive definite. Okay, so second derivative negative definite, inverse of it, and taking the negation, that gives us a matrix which is positive definite. Of course, in practice, if you are doing some SGD optimization, you may not have gotten to the local maximum. So the second derivative could end up being not negative definite. So it could be it could have both positive and negative eigenvalues. So people have done things like approximating this second derivative using the generalized Gauss-Newton approximation, for example, which is always negative definite. Okay, and that is something which is quite interesting. I'll come to a bit later. Okay. Right. So, and this Gaussian approximation works pretty well when you have lots of data, and if your model is not too high dimensional compared to your data, which of course this is not true in practice nowadays. But yeah, if your n is much bigger than your dimensionality of theta, then you can show that the covariance here shrinks at the rate of 1 over n, simply because the second derivative is a sum over n terms. Okay? And the quadratic approximation actually gets more accurate for large n. Okay? So this is something from probability theory called the Bernstein-von Mises theorem. Okay? Right, and what that says is that the Laplace approximation will get better and better as your data set increases, gets bigger and bigger. And you can also make predictions under this Laplace approximation. Basically, we integrate over theta under this Gaussian approximation. Okay? This can be quite accurate, particularly since the posterior is going to be approximately Gaussian for large n. But in practice, what happens is that because of the high dimensionality of theta and the non-linearity of the neural network, actually this is still makes this basic Laplace approximation actually very challenging. And in fact, the predictive distributions under this Laplace approximation actually doesn't work as well. Okay, so I'll come back to this at the end of the lecture. So, so people had actually explored this. In fact, the first people who started thinking about Bayesian neural networks were people like Dave Mackay. This is one of the first methods that he developed. This is 30 years ago now. Okay. Right, and since then, people have thought of different approximations. Okay, so there are two popular classes. One is called variational approximation. And in variational approximation, we actually try to formulate the computation of the posterior itself as an optimization problem. Okay? But now, instead of over the space of parameters, it's going to be an optimization problem over the space of distributions of our parameters. Okay? And basically, what you can show is that the true posterior is the argmax over all possible distributions of Q over theta of this quantity here. Okay? And you can think of this quantity here as basically this is the log likelihood, okay? And that's the prior. And basically, this is the expectation under our putative distribution over theta of the log likelihood and the prior. And then we also need an additional term which actually regularizes the problem so that the maximum isn't just the maximum a posteriori theta, isn't just a delta function at the maximum a posteriori theta. That the maximum is actually a proper distribution. We need to regularize this, okay, using basically the entropy of Q. And you can show that this is a nice algebra exercise if you haven't done it, that the distribution which maximizes this quantity is simply the actual posterior distribution. Okay? And that objective here is in fact lower bound on what's called the evidence, or which is simply the marginal probability. Okay? So again, this is a bit of exercise. You can show that the log of the marginal probability of observation y given x. So this is log of an integral over y given theta and x and over the prior. Okay? And you can introduce a q here and then pull in the integral inside the log. Sorry, outside the log. Okay, yeah, pull out the integral outside of the log, and then you get that quantity. So this is just Jensen's inequality. And you can show that this objective function is a lower bound on the marginal probability of interest. Okay. Right. And so once you have this objective that you want to optimize, we can do all sorts of approximations. So for example, we can approximate our Q distribution using a Gaussian with some mean and variance. And when we want to maximize over Q, what that corresponds to is simply maximizing with respect to the parameters of Q, which is now the mean and the covariance matrix. Okay. So this is something which was proposed by Charles Blundell et al., I guess about 9 years ago now, and this uses standard deep learning optimizers and something called the reparameterization trick, okay, which was developed originally for VAEs, but it has been used for Bayesian deep learning as well. Okay, cool. Right, so just a few words on variational approximation. People don't use it that much nowadays because it turns out that actually it doesn't work as well as other methods. So the first one is that you can rewrite this elbow, the evidence lower bound, in two different ways, which gives you a bit of insight about what variational approximation is doing. Okay. So the first one is that basically, if you look at the expectation of Q of the second and the third term, that's just a KL divergence between your putative distribution Q and your prior. Okay? And then the first term is just the expectation of the log likelihood. Okay? So when we want to optimize this thing, you can again think about this as some regularized optimization problem. We are regularizing our putative distribution towards our prior. That makes sense because we want our distribution to be close to our prior. But we also want our distribution to explain our data well, and it is this term which says that distributions which are good under this objective should also explain the data well. Okay? So it's a balances between a data explanation term and the prior term. A different way of writing the exact same equation is that you could show that the objective here, which is the elbow, is equal to, we know, is the log marginal probability of y given x minus a KL divergence, but now instead of towards the prior, it is towards the posterior. Okay? And what that says is that it also makes it clear that maximizing the elbow is the same as minimizing this KL divergence, And if you can optimize over all possible distributions of Q, then of course the one value of Q which minimizes this KL divergence is simply going to be the posterior itself, at which point the KL divergence is going to be exactly 0. Okay. It's also quite useful to think about this in that the KL divergence is not an actual distance measure between two distributions. That's why it's not called KL distance. It's called KL divergence because it's not a distance metric. And it is asymmetrical. Okay? So the KL of Q to P is not the same as KL of P to Q. Okay? And particularly, a KL of Q to P like this will penalize large values of Q when the P is actually small, when the posterior probability is actually small. Okay? So what that means is that variational approximations tend to also undercount uncertainty. Okay, so the visualization of this is the following. Imagine that your posterior has two different modes. You have one mode like here and a second mode here. Okay, and if your Q distribution is, let's say, a Gaussian, it's just a single mode distribution, then you cannot really have a Gaussian which covers those two modes. Because if you do that, then the in between the two modes where you have low probability under P, you have high probability under Q. Okay? And the KL divergence penalizes that a lot. So you can show that if you have this two-mode posterior, then the Q distribution will simply concentrate on one of the modes and just ignore the other one. Okay? So it captures uncertainty around that mode well, but not the other modes. Okay? And it turns out that oftentimes, when you want to capture this uncertainty better in terms of making good predictive distributions, you should account for the different modes, which is why actually deep ensembles works a lot better than the variational approximation for neural networks. Okay, because in deep ensembles, you initialize the parameters at very different parts of the space, and each of them gets to a different mode. So when you average over them, you get actually you capture better in the uncertainty in the actual process itself. Cool. So that's variational approximations, right? So this is thinking about, again, the problem that we want to solve, which is to get a handle on the posterior distribution, and we are rephrasing it as an optimization problem. Okay. There's a different class of methods called Markov chain Monte Carlo methods. Okay. This is actually a really big class. Actually, the first Markov chain Monte Carlo method is called the Metropolis algorithm. Have you guys heard about the Metropolis algorithm? Yeah? Okay. Basically, it was developed in the US by actually a whole bunch of scientists, apparently not including Metropolis himself. He's the manager. But his name is on it. But basically, they used it to model nuclear fission, basically. Okay? To understand how does basically to develop the nuclear bombs. Okay. Right. So we have our posterior distribution of interest, and we have a predictive distribution, which is an integral under the posterior of the predictive of y given theta, right? And you can of course write that thing here is simply the expectation under the posterior. Oh, I'm sorry. So this should be theta of p of theta given x and y, okay, of the predictives, okay. And if you have samples from the posterior distribution, then you could approximate this expectation by a Monte Carlo estimate, okay, by basically if you have IID samples. It is of course still difficult to obtain posterior samples. So Markov chain Monte Carlo is a way of getting approximate posterior samples by running basically something called a Markov chain forward in time. Okay. Nowadays, it's still of interest in terms of these Markov chains because diffusion models, if you think about it, is a continuous time Markov chain. Okay. Right, but I will just tell you a very simple MCMC, Markov chain Monte Carlo method called stochastic gradient Langevin dynamics. Okay, it's very simple. Basically, if you take the SGD algorithm, okay, so this is, each iteration looks like this. And you can show that as the learning rate goes to 0, this thing at some appropriate rate, then this thing will converge to a maximum a posteriori theta, okay, a single value of theta. If we do not want that thing to converge to a single value of theta, but rather to a whole distribution over thetas, what you could do is to just add some noise. Okay, so if you take the exact same SGD update and you add some noise, which is Gaussian distributed with a 0 mean and with a variance which is associated with the learning rate. It has to be twice the learning rate. Okay? And if you do that, and as the learning rate goes to 0, you can show that the samples of theta that you get in the end at convergence will not stay put on a single value, but rather would bounce around. Okay? And basically, you can show that they, in fact, will bounce around the posterior distribution. Okay? And yeah, so this is, I guess, something that, you know, the physicists have looked at. This is called the, I think, overdamped Langevin dynamics. Right, and that's why we call this stochastic gradient Langevin dynamics, because it's not really the gradient, but rather we're using a stochastic gradient. Okay. But this is just one of many methods. In fact, in this class here, there's a really nice paper by Whye Ma and Emily Fox, where they kind of developed a whole class of stochastic gradient MCMC methods, okay, including stochastic gradient, Hamiltonian Monte Carlo, and so forth. Okay, so in general, in Markov chain Monte Carlo, we have some Markov chain. So we have basically a generative process, theta 1, and then theta 2 given theta 1, theta 3 given theta 2, and so forth, with some Markov transition kernel, which describes each conditional distribution of theta t plus 1 given the previous value of theta. Okay, and this is your Markov kernel in the case of SGLD. Okay, and basically you can design lots of different types of Markov transition kernels such that the Markov chain will converge to the posterior for given a large number of iterations. And you also want your Markov chain to mix well as well, i.e. it converges fast to the posterior distribution. Okay. And then once you have the Markov chain, you can simulate it, and then you can just approximate the averages under the posterior, including the posterior predictive, by basically this Monte Carlo estimate. Okay. Right, there's a huge range of MCMC algorithms out there. Yeah, most of it has been kind of developed more in the statistics context. But if there are some of you interested in, for example, probabilistic programming, it's basically most probabilistic programming systems these days that are successful use Hamiltonian Monte Carlo, which is a generalization of Langevin dynamics. Okay. And there's also a nice paper by EEML'24, who basically managed to kind of run Hamiltonian Monte Carlo to get actual samples from the posterior distribution. Okay, so that's MCMC sampling. Okay, I think, I'm running out of time. I want to say a few words about neural network Gaussian processes and then come back to Laplace's approximation. Okay. You guys are probably familiar with different initialization schemes, right? Although, did we talk about initialization schemes yesterday? No. It turns out to be really important to get neural networks to work. But of course, nowadays, it's all built into PyTorch, JAX, and so forth, so you don't actually even have to think about it. But it took people quite a number of years to figure this out. Basically, if you have, let's say, an MLP, and if you have one of these weights, it turns out that it's important to initialize the weights in such a way that basically the activations, both the activations and the gradients don't either blow up to infinity or go down to zero, okay? So this is actually a theory called signal propagation theory for neural networks. And basically, people worked out that the way you should do this is to initialize the weights to be basically pretty much normally distributed, potentially with some clipped tails, with a mean of 0, and a variance, importantly, which scales as 1 over n, which is the number of incoming units to each layer. Okay. And if you think about this as a prior distribution over your parameters, okay, you can actually show that the neural network function, f theta here, actually converges to something called a Gaussian process in the limit where the number of units in the neural network goes to infinity. So this is the infinitely wide neural network. Okay. And basically the GP kernel, so this is kernel in the sense of kernel learning, is defined by the neural network architecture. And this was actually already derived by Radford Neal in about 30 years ago. Okay, so this is a long time ago, and it gave rise to a whole field of Gaussian processes in machine learning. So if you're interested, there's a book by Williams and Rasmussen. And the interesting thing with this GP view is that in this infinitely wide limit, you can also show some pathologies in the learning. Okay, in particular, if you now do SGD in this infinitely wide neural network, it turns out that only the last layer weights will actually change at all. And all the previous layer weights will just stay at initialization. So this is what's called a kernel learning regime, okay? Which in a sense is not good because you want your neural network to learn features of your data, from your data, and to adapt those features to the data, rather than to just initialize them at random. More recently, there's a very nice paper by Jacquot et al. And then there's also a follow-up paper from Google Brain, Lee et al., where they used a slightly different parameterization of the neural network. In fact, it's kind of like trivially different, but it is actually leads to a different learning dynamics, which kind of goes to show that, you know, these things have to be very careful with how you initialize, how you parameterize your neural networks for your learning to work well. Okay. In this parameterization, your weights are going to be actually drawn from a standard normal. But when you compute the activations at the next layer, you want to take the activations in the previous layer, multiply by the weight matrix, and then you divide by the square root of the number of input units. And then you add a bias, pass through a nonlinearity. Okay? And this, of course, is exactly this, if you think about it, is exactly the same as that initialization. It's just that you pull the 1 over n out of the weights, and you write it into the activations instead. Okay? But what they were able to show is that this actually allows all the weights to be learned in this infinite width limit. Okay. But the learning is still a kernel learning regime, but now the kernel matrix is what's called the neural tangent kernel. Okay. And basically what this thing is equivalent to, which is what the second paper shows, is that the learning dynamics is equivalent to actually learning in a linearized neural network, which is linearized around the initialization. Okay, so just to be clear, so we have our neural network, and theta naught is the initialized parameter, is the initial parameters, and instead of treating f theta of x as some nonlinear function of theta, we're going to do a first-order Taylor series approximation of that around the initialization. So this is a linearized f at theta is going to be equal to basically so this is the 0th order term, and that's the first order term. Okay. So this is just first order Taylor series expansion. And in this case here, the linearized neural network is a non-linear function of x, but it's a linear function of theta, because you've kept the initialization fixed. Okay. Yeah, so, and I mentioned this because it turns out that this idea of linearizing a neural network turns out to be really powerful, and it has been applied to the Laplace approximation. Okay. And this is what's called the linearized Laplace approximation, which turns out to work really, really well. Basically, instead of linearizing your neural network at initialization, you should first run a standard SGD first, get your map estimate of your parameters, and then you linearize around that map estimate. So the idea is the initial learning of your theta star learns your features, and then you construct a linear approximation of the neural network around that learned features, and then you do your Laplace approximation. And because your function now is linear in theta, actually the Gaussian approximation works really well. Okay? And interestingly, under this linear approximation, the Hessian here turns out to be the generalized Gauss-Newton matrix. And this works much better. Okay? So if you're interested, you can look at some of these recent papers from Immer et al. And Antoren et al. But there's also a whole bunch of other papers as well, which I haven't referenced. Okay, so I'll conclude there. Basically, Bayesian deep learning is a very active, I think, and fertile area of research. There are lots of interesting, strong connections to other areas in machine learning, including Gaussian processes, learning dynamics in neural networks, signal propagation theory, and so forth. And also, of course, true Bayesian statistics to other fields as well. There's lots of other things that I haven't covered. Probably the most important one is possibly function space perspective in Bayesian deep learning. So in Bayesian deep learning, oftentimes people assume that the parameters are just drawn from an IID Gaussian, the initialization distribution. But of course, that turns out to be a bad idea because it doesn't really reflect what we think of as sensible notions of like smoothness in our functions and so forth. So there's been lots of work around actually constructing priors and optimizing your neural network in this function space view rather than in the space of parameters. Okay, thank you.
So maybe we have time for a couple of questions. I wanted to start with one from Slido, just to
okay.
the ones that are online. So the question is, LLM kind of work? Should we expect like Bayesian LLMs soon?
There has been some work on Bayesian LLMs. There's one recent paper from Lawrence Atchison, where basically you take an LLM. So the issue of Bayesian anything is that computational cost is expensive, right? So LLMs, even bigger model, computational cost is going to be even exorbitant. So what they did was they, as expected, you take your LLM, and people don't fine-tune the LLMs directly. They might do parameter-efficient fine-tuning like LoRa, and basically they did Bayesian LoRa. But to actually get it to work is actually quite tricky because you have to account for how do you estimate the covariance in your Bayesian posterior and so forth. So, and there's quite a lot of technical details in terms of deriving that. Yes?
I have a question slide before, please.
Yep.
Yeah, the linearization and when you're calculating the hashing in the second line.
Yeah.
How far are you going into the dimension of these calculations?
Yeah.
How big vectors?
Yeah. So what people do is, so if you just derive this, it's of course going to be a matrix which is going to be D by D, where D is the number of parameters of your neural network, which is of course not going to be tractable. So people have done things like Kronecker factorization, where you approximate that D by D matrix with block diagonal matrices, each block corresponding to each layer, and then you even have approximations within that layer as well. And yeah, that works well. But it does get quite hairy, I think. Yeah.
And any errors on the Gaussian when it's diagonal and not diagonal?
Yeah. So it will be additional approximations. So every time you have to make it even more efficient, you have to do even more approximation. So the question is, how do you find that right trade-off between computational efficiency and, I guess, capturing more of that posterior uncertainty?